So what is C of 0 is going to be one question. What is C of 1? Well, C of 0 is equal to C of 0 by the functional equation. We call C of S. And C of S is equal to 1/2 SS minus 1 pi to the minus S over 2 gamma S over 2 theta S. So we have to calculate this thing at S equals 0. So C of 0 is going to be the limit S goes to 0 of this thing. But I will write this as 1/2 pi to the minus S over 2 S, sorry. Here I'm going to put S over 2 gamma S over 2 S minus 1 theta S. So limit, actually from here, C of 0, I have to calculate same as C of 1. So I really should be doing this. Everybody following what I'm doing? C of S is this function. I want to calculate C of 0. But that's the same as calculating C of 1 by the functional equation. And C of 1 is equal to limit as S goes to 1 of this object. The advantage of this is that S minus 1 zeta S now, limit is 1. And S over 2 gamma S over 2 is just going to be, well, everything else is well behaved at S equals 1. So C of 1 equals 1/2 gamma of a half pi to the minus 1/2. Something is fishy. I should get 1. I'm getting a half. Why am I getting a half? Oh, thank you. What are you saying?
That 2?
Where? Oh, this was 2. Thank you.
But we have not used here.
Well, I think she's right. There was a silly 2 floating around, okay? That's what you say, but I think I think it really is, there's a 2 there, yeah. And so this was 2 times C of S to start with.
But where we are using only, sir, we are applying just xi of S, still we have not gone to that formula.
Which one?
We are just using here only. Yeah, definition for xi S only we are using. We have not gone to the Mellin transform.
No, I agree. But I want to get C of 0 to be 1.
Yeah.
Got cancelled when we changed y to y squared.
Yeah, the 2 got cancelled when I changed y to y squared.
Yes.
Too bad I don't have the paper with me, but
No, even if it is.
there was a 2 there. There was a 2 there to start with. Yeah, I think you guys are right. Remember theta of y minus 1 divided by 2, and there's another 2 that went out there. Okay? So let's put the 2 back in.
Oh.
so that when I have a half here, so gamma of a half is root pi, and so that kills this thing that's a half here. So that means I get integral 0 to infinity h of y at y to the, at s equals 1, which means dy, and that's the same as the integral from 0, h of y over y dy, everything equals 1. Okay, I need to get it equal to 1. That's the main reason of putting that stupid half at the in. There was really no real motivation earlier to put it there, because this had a functional equation. Whether it's a constant, it doesn't really matter. It'll still have a functional equation. But why did you put it there? You put it there because you want to get a 1 here. Okay, and in some sense that makes sense, because now this is a probability. So h of y is now not only non-negative, but it integrates to 1, and therefore you can interpret this as a probability distribution. Thus, if y is a random variable with distribution h of y, then the expectation of y to the s is nothing but the Mellon transform, so 0 to infinity, y to the s, h of y dy, which, let's see, what do I have here, dy? Yeah, so, yeah, that's correct. So we can interpret it, this thing as, oh, yeah, sorry.
Minus 1.
I want to say h of y over y, because h of y over y can also be thought of as a distribution. So let y be a random variable with distribution h of y over y, then I can put this y over here, and this will be C of s, or 2 C of s, as you were trying to tell me. Here. So whatever it is, 2 times C of s has been interpreted as the expectation of this random variable, and so this gives a probability interpretation of C of s, not zeta of s, C of s. So what is the value of all this stuff? So far, this is very interesting. We have a probability interpretation of this thing. Good. Now, recall the following. Given the random variable x, the moment generating function defined as expectation of e to tx. So it's the definition of the moment generating function. And e to the itx was the characteristic function. And now I'm going to define what's called the cumulant generating function. Is log phi xt. The log phi xt is has an expansion in terms of case of n t to the n going from 0 to infinity, so it has power series, and the case of n's are called cumulants. It's called the case of n is called the nth cumulant. It's called the nth cumulant. Okay, so that's the definition of the cumulant generating function. And now I want to study what this has to do with the zeros of the Riemann zeta function. Now, keep in mind the difference between C of S and zeta of S. C of S, interestingly enough, is an entire function because of that S minus 1 factor. Yeah. Also, you all probably know that the Riemann zeta function has trivial zeros at S equals, minus, what is it, minus 2, minus 4, dot, 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 right? Those. Is that correct?
Yeah.
And therefore, the point about C of S, though, is it has no trivial zeros. All the action of C of S is happening inside the critical region. There's no trivial zero business because they were cancelled by the gamma function. The trivial zero of the poles of the gamma function cancel it. So the only zeros of C of S are the non-trivial zeros of the Riemann zeta function. Okay, that's the one advantage of moving to C. Yeah. The only zeros of C of S are the non-trivial zeros. That is zeros rho such that real part of rho is between 0 and 1. We know there are no zeros.
So it is cumulant generating function. So this is just a notation?
It's just notation. Yeah.
It is not logarithm of that function.
It is. You just take the log of this function.
Could it be this?
For example, we calculated the the moment generating function of the normal, right? And what was it? E to the minus t squared over 2 or something. And so the log of that thing will be the cumulant generating function. Pardon me? X here? No, x is just a random variable. And so phi x is just either t, so this would just be, the formal power series. So you have t to the k over k factorial, and this will just be the expected value of x to the k going from 0 to infinity, just as a formal series. And these will be the moments, right? These are the moments of the function. So you have the moment generating function starts off with 1 plus higher moments, and then take the log of that as a formal series. You get, log of 1 plus something as an expansion, and those coefficients are called cumulants. At the moment, there's no issue or discussion about convergence. Where this silly thing converges, we're not going to talk about that, but that just generally generates in a formal way the formulas for these cumulants. Yeah. So you can then see that the moments are connected to the cumulants, just because of, you got this by taking log. So there's gonna be a connection that's gonna come out, yeah. Now, the zeros of the C of S are the non-trivial zeros of the zeta function, and you all know about Weierstrass factorization for analytic functions, or slightly better than Weierstrass, I guess, suppose, in this case, is the Hadamard factorization. So we have the Hadamard factorization. S is now I should tell you that the factorization works like this because this function is what's called function of order 1. The growth rate means you may remember from your Weierstrass factorization theorem that it's more complicated in general, and it depends on the convergence of 1 over rho squared. Well, here you can do a little bit of calculation and show that you have to do a zero count for some growth condition. Either you do a zero count or you use the definition, Stirling's formula in the complex notation to show that this is valid. So this, you don't have extra terms, just have something like this. Now, C of 0, we just finished calculating. I remember I was very adamant putting C of 0 is 1. Okay? No, C of 0 is 1. I was trying to get C of 0 to, well, 2, well, okay. Do you want me to, okay, just delete, get rid of all this discussion by just shoving a 2. That's irrelevant discussion, okay? What, okay, let me make, let's call this, C star or something, I don't know. Okay, let's see. 2 C of 0 is 1. And therefore, when I plug in S equals 0, all these disappear. And you get E of the A is 1. E of the A implies E of the A is 1. So therefore, this term isn't there. I'm using rho for zeros of zeta function, the standard notation, so just keep that notation rho. And I'd like to now get rid of this B. So take logs and differentiate. That stupid 2 will go away, okay? What happens? Well, I get a B. Oops, this is log, sorry. This is log. This is log 2 plus log C of S, right? And then now differentiate. Oh, so there's a DS.
Yeah.
Now differentiate. So cancels 1 over 1 minus S over rho minus 1 over rho plus 1 over rho. So what do we get? We get B plus summation rho. Well, the rho's cancel. It's a rho minus S, but there's a minus sign, so it's 1 over S minus rho plus 1 over rho. Look at this expansion for this. C of S, C prime of S over C of S is this. Now, we have a functional equation. On the other hand, C of S is equal to C1 minus S by the functional equation. Therefore, taking logarithmic derivative of both sides, you get this. Right? But I have an expansion of C in terms of the zeros. This is valid for all S in C, except for those complex roots. So I can plug in 1 minus S in here with a minus sign. So we get B of summation rho 1 over S minus rho plus 1 over rho equals minus B minus summation rho 1 over 1 minus S minus rho plus 1 over rho. Right, I plug in 1 minus S in this expansion. So what is this? It gives us a nice equation. It gives us 2B plus 2 times summation. By the way, don't worry about this convergence business. You can always truncate and take limits, okay? As t goes to infinity. So we'll get 1 over rho here. So I've got summation 1 over rho on this side, and another minus, so it goes to the other side, and I get this. And then now I take this, and I do 1 over, minus 1 over S minus rho. And this time I'm going to put a plus and change the sign of this to be S plus 1 minus rho. You follow that?
Plus rho minuses?
I put a minus sign here, S, minus 1, thank you. Is that what you meant?
Yeah, plus rho, plus rho.
I want to cancel those things, okay? But everybody okay with this? Now, as rho runs through the zeros, 1 minus rho also runs through the zeros by the functional equation. Therefore, whenever there's a term, it gets canceled by this guy. So this is 0. Since rho and 1 minus rho are both zeros. So get rid of, so B, the B business here is B equals minus summation rho 1 over rho. Okay? And now, because B is minus one over rho over, I can now use that, this B, and this gets cancelled. And so therefore, this implies everything disappears. Of course, we will ignore questions of convergence. If you want to worry about it, you pair up rho with rho bar. Okay, and then in these infinite products. So that's it. 2 CFS is this has got to be the simplest. It's like a polynomial factorite. What is a polynomial? F of x? Well, it's product x minus rho, where rho's are the roots. This is the version of that. See, all these, usually you have these complicated factors, they're all gone. They're all gone by this analysis. But they're really not there. That factor gets killed by this guy. And so you get a very neat thing. I think this is where Lee starts from.
Into the S by rho, no?
What is it?
E to the s by rho cancels with the e power bs, right? B is like a summation 1
B
by
is
rho.
this. And it appears with a minus.
It's appeared with a minus. That's it.
This is an important punchline. Okay, so you get something like this. And as I said, if you're worried about convergence, you would really normally pair up rho with rho bar, and then continue. Yeah. Now, here's a little. I suppose one of the motivations for Lee's work is this particular thing, and the other motivation, I suppose, for Lee's work is he was certainly motivated by algebraic geometry, and he was trying to figure out why hasn't this been formulated in terms of the way the geometers formulate the Riemann hypothesis. So one of the elementary observations is essentially based on the theory of conformal mapping, but let me just make this elementary observation so that it motivates some of the change of variables that Lee does. So let me just, rho is a complex number, it's not a zero now, okay? Just a silly complex number. Sometimes some very elementary observation, if you have it, everything makes sense. If you don't have it, you don't see where this guy's getting this thing from. So this seems to me to be the most elementary observation, and the proof is very easy. Let me do it because it's easy. Rho, let's write as x plus iy. Then rho minus 1 is x minus 1 plus iy. And rho minus 1 absolute value squared equals x minus 1 squared plus y squared. And absolute value of rho squared is nothing but x squared plus y squared. So keep in mind this is x squared minus 2x plus 1 plus y squared. So what are we saying? We're saying rho minus 1 absolute value squared is less than rho squared if and only if minus 2x plus 1 is negative, which means x is bigger than a half. Okay, so this is true if and only if this happens. Why would we care? Well, that's, if rho is the zero of the zeta function, this is what the Riemann hypothesis is all about. And so this gives rise to the idea of some sort of conformal map of moving the half plane of, real part s bigger than a half into a disk, basically the disk given by rho minus 1 divided by rho, and saying saying that essentially if I make such a transformation, the Riemann hypothesis then will be equivalent for all the zeros to lie in a certain disk, instead of infinitely many zeros on the vertical line type of thing. So then maybe you can bring in usually theory of power series into the picture. Okay, so this elementary observation in hand, we then go back to this consider C of S over S minus 1. You now know why you do that, because rho over rho minus 1 is bigger than 1. And so if, we would try to look at this mapping. So I'm just trying to motivate some of the calculations of Lee. And this is easier than Polya's motivation, because Polya doesn't give any motivation. So this now gives me product rho here, 1 minus S over rho, is a simply 1 minus S over S minus 1 rho. C of S over S minus 1 is equal to product rho 1 minus S over S minus 1 rho. Now if I call this, I think phi of S for a moment, we may come back to it. Let's just analyze the product on this side, and don't worry about convergence. What do I have? I have S rho minus rho minus S, which equals product rho. I'll just put the two S's together. Let's see, S minus, sorry, I'll do, S minus 1. Rho, S minus 1. No, I don't want that. I want rho basically what I want to get is 1 minus 1 over rho S. That, how do I do that?
You can cancel the row in the numerator and denominator.
I can cancel the row in the new, yeah, thank you, yeah. So cancel the row in this thing, yes, and then I get that. Thank you, yeah. Okay, yeah, so cancel that, then it becomes 1. Wait a minute, I get, no, I don't get that. Hold on. No, just hold on for a second. This will keep. You want to cancel the row in the numerator and denominator, then all I'll get is.
Yes, if we take out then rho minus 1. Yes, we take out then rho minus 1.
Yeah.
Then
Yes, we
you
take out and rho
also.
minus 1.
Then you take out rho also.
Yes.
Rho you take out.
Yeah,
Rho.
this equals rho minus 1.
Minus.
And then plus rho? No, minus rho.
Minus rho. You take out rho. No, rho he wants to cancel. Kind of if we take out.
We have minus 1 missing.
I'm supposed to get S over S minus rho, S minus 1 over rho. So, yeah, I got that. We got this, right? So this is supposed to be 1 minus 1 minus 1 over rho S on the numerator.
Okay.
Is that?
Yeah,
Is that
1
correct?
minus S.
Is it a 1 minus S?
Yeah, minus was the trouble.
Oh, minus was the problem.
Yeah.
So let's just see. Does this work out? So this
Yeah.
this becomes 1 minus S and 1 minus 1 gets cancelled, right?
Yeah.
And
if
then
you just multiply by row, then row will come down below.
if I multiply what?
No, there.
So here,
Numerator.
yeah, multiply by row,
Row, both ways,
Row.
both sides, then you get the same.
with a sign
Yeah.
difference and yeah, so okay, so that's basically the idea. So this comes out to be product row 1 minus 1 over row S,
There will be 1 minus.
pardon me, is that right?
1 minus S.
One minus.
Oh, 1 minus S, 1,
No, below.
Denominator.
Denominator.
oh, denominator is 1 minus S.
1 minus.
One minus. Thank you. Yeah, so the idea is to get, actually, that should have been clear, because I want to make it into geometric series, because I'm going to take logs, yeah. So, okay, now that we have this, if I take log of phi of S, log C of S over S minus 1 is equal to summation, as I said, don't worry about convergence business at the moment, log of 1 minus 1 over row, S minus log 1 minus S. Fair enough? And then we know that log of 1 minus 1 over row, S has an expansion in terms of Taylor expansion. So my summation minus 1 minus 1 over row to the n, S to the n over n, n going from 1 to infinity. And log of 1, so this is minus log of 1 minus S, has an expansion going from 1 to infinity of S to the n over n. So in other words, log of 1 minus, log of phi of S is equal to this expression here, and minus log of 1 minus S has this power series, and log of 1 minus 1 over row S has this power series. Therefore, the power series expansion of this thing is equal to 1 summation row 1 minus 1 over row to the n so log of phi of S, which is the same as log of this C S over S minus 1, is equal to this expansion, where these are your famous lambda n, the Lie coefficients. So these are your Lie coefficients. Okay? And because I said that C of S has a probabilistic interpretation, and you have, I told you that C of S is equal to the expectation of Y v S. You, since I'm running out of time, I'll just maybe mention what I'm going to do tomorrow. So you have a probabilistic interpretation of this thing. So now, essentially, after a certain change of variable, I'm taking logs, and so this should be related to some sort of cumulant generating function. So there must be a relation between the cumulants of this particular distribution and the lambda n's that are appearing in the Lie coefficient. And as I mentioned earlier, I'll try to show how this works next time. The Riemann hypothesis is equivalent to the lambda n's being always positive. And we'll work out next time what at least lambda 2 is, and then interpret it probabilistically as a variance, and therefore it's non-negative automatically. So, but the interpretations for these higher lambda n's is missing. And that's where we're all stuck at the moment. And we'll talk about that maybe tomorrow.